Yeah, in the next couple of minutes before lunch, I would give you a short overview about the new developments with the Kepler architecture and also new developments with the GPU computing ecosystem. I'm sure you know Nvidia as a supplier of the GPUs in the consumer market, the GeForce, the Quadro for professional graphics, and also the Tesla for supercomputing. You know that we have the Tegra processor for the mobile space, for tablets, for smartphones, etc. I want to highlight here on this slide two new developments we are focusing on. This is a so-called GeForce Grid or GeForce Cloud. So gaming is moving to the cloud. There is a trend not to install the games on the local PC. The trend is to install the games on a central server farm and to run the games by remote and controlling these games with a console like the Shield console Nvidia announced some months ago. Another trend is the so-called VGX technology we are working on. So it's a trend to centralize the visualization, the graphics capability into a central server and to virtualize the GPUs in a similar way like you do with the CPUs today. So that's the VGX technology with the K1 and K2 boards we have announced. Coming back to supercomputing, the Kepler architecture has two different product lines. That's the Tesla K10 based on the so-called GK104 Kepler chip. And this K10 is focused on single precision performance. So for dedicated markets like oil and gas or in the defense and government area where single precision performance is needed and they don't need double precision performance for time migration algorithms or signal processing, video analytics or image processing. So the real double precision focused GPU is the Tesla K20, K20X based on the GK110 chip. And with this GPU, we are addressing supercomputing like weather, climate modeling, molecular dynamics, or also life science codes and manufacturing structural mechanics like abacus, electromagnetics, or CFD codes. Here you see an overview about the specification of the different GPUs. So the K10 is a dual GPU board with two of these GK110, GK104 chips and provides you roughly 4.58 teraflops from a board point of view to 2.3 teraflops per GPU and SGEM performance of roughly 3 teraflops. You see double precision performance is very low for this board. So if you have double precision algorithms which needs double precision, that's not the right choice here, the K10. We have 2 gigabytes per GPU, 8 gigabyte per board, 160 gigabyte per second memory bandwidth. We are supporting features like GPUDirect RDMA, which I want to cover later. And the K10 is a passive cooled board, so there is no fan on the board, so the server has to cool this board. The K20 and the K20X are based on this GK110 chip. The difference is the number of SMs we are supporting in the K20 and the K20X. K20 has 13 SM streaming multiprocessors, and the K20X has 14 SMs supported, which provides you more double precision flops. So in this case, 132 teraflops versus 170 teraflops. And the other difference is the memory size. We are supporting with the K20X 6 gigabyte of GDDR memory instead of 5 gigabyte for the K20. And with one less memory channel, we only support here for the K20 a little bit over 200 gigabytes per second, and with the K20X 250 gigabytes per second. So from the features point of view, it's the same GPUDirect, Hyper-Q, dynamic parallelism. I will come a little bit later to these features. ECC support is the same for K20, K20X. A little bit higher power consumption for K20X, and the form factors are the same regarding passive cooled and SXM. For the K20, we are also providing an active cooled board, the K20C, with the same specifications here, but with a fan on the board. Regarding the parallel computing platform, here we have on the hardware side powerful SMX streaming multiprocessors. We are supporting with these GPUs hardware features like dynamic parallelism, Hyper-Q, or GPUDirect. On the compiler side, I want to focus later on this open compiler tools based on LLVM compiler suite. And we have, of course, CUDA language and the OpenACC compiler from Cray, PGI, CAPS. Development tools, a lot of Nvidia tools with a parallel inside development tool suite, the visual profiler, the debugger, but also third-party tools like DDT, TotalView, or Vampire from University of Dresden. And you have different approaches to get the GPU performance into your applications. So that's a drop-in support for libraries. You can change the libraries you are using on the CPU side with a GPU-optimized library. You have the programming languages dedicated for the GPU, the CUDA language, for instance, which gives you the maximal performance. And you have the OpenACC directives as a very easy programming paradigm to start with the application porting. Some of the Kepler features which are new is the Hyper-Q feature. So with the previous generation, with the Fermi generation, you had only one so-called working queue, so which means only one CPU process could use the GPU. And if this process started a kernel which was not very compute intensive on the GPU, the utilization of the GPU was very low. So with Kepler, we have up to 32 concurrent working queues. So this means up to 32 concurrent applications, concurrent MPI ranks can use the GPU, and which gives you a much higher GPU utilization, of course. Another feature we introduced with the Kepler architecture and with CUDA 5 is a so-called dynamic parallelism, which gives you the possibility to write much simpler code because with Fermi, you started your kernel to the GPU, and the GPU had to give back the results, and you had something like a ping pong between the CPU and the Fermi GPU. With the Kepler architecture, the GPU is now able to launch their own work so that you can run more or less the whole application here on the Kepler GPU, which gives you a lot of advantages, for instance, for adaptive algorithms, etc. So you don't have this ping-pong game between the CPU and the GPU. The hyperQ feature for MPI will be addressed with the so-called CUDA proxy or MPI proxy. What does it mean? You have a proxy server running on the CPU, on the host, and all the MPI ranks on this node funnels their request for the GPU to this proxy server, and the proxy server schedules the work to the GPU. So this means you can run more than one MPI process on the GPU at the same time, and with only the proxy server accessing the GPU, you have only one context on the GPU, and you don't have all the context switches on the GPU when you would have all the other kernels with other contexts running on the GPU directly. It's currently working on a Cray. It was a focus, of course, to implement this on the, for instance, Titan system. But with the next generation, the CUDA 5.5, it will be available for all the Linux distributions we are supporting with the current or with the CUDA version. We heard about GPUDirect RDMA from DK Panda, and we saw first results. So GPUDirect is a very nice mechanism to enable the communication between the GPU in different nodes. More or less, the GPU memory will be implemented or will be shown in the PCI Express bar window, and the network card can access this memory directly. But it's not a solution which only works for network cards or something like InfiniBand or other network implementations. It's a general approach and can also be used, for instance, in conjunction with other PCI Express devices, for instance, flash memory devices. And we were working with companies in order to implement something like a flash memory device for GPUs. We, of course, want to broaden the ecosystem for the GPUs. Therefore, we changed our compiler suite 1.5 years ago from Open64 to the more modern LLVM compiler suite. And this gives us availability or the possibility to support new languages, new domain-specific languages on top of this LLVM compiler, and gives us also the possibility to address new backends, new processors with, for instance, a CUDA language. Here are some examples. We are looking on or we are working on, for instance, Java, Python, R is a statistical language, or other DSL languages, and as a target processor, ARM, of course, FPGA, other GPUs, x86, Xeon Phi, etc. Here you can see the open compiler architecture we introduced for the first time in CUDA 5.0. So you see here the chain in the compiler architecture. You have your front end here, the libcuda.lang. You have then a step with the LLVM optimizer, code generator, and this generates PTX code, which will be assembled, and together with the host code, it will be compiled and can run on the CUDA runtime with the CUDA driver. So the LLVM optimizer and the code generator is part of this so-called CUDA software development kit, which can be downloaded from this website here, CUDA LLVM compiler on the developer Nvidia side. And we also made available this code generator and provided this code generator back to the LLVM compiler suite, so that is integrated part of the LLVM compiler suite, which you can download from their website. Some scenarios for using the compiler suite. I mentioned front ends you can build with the compiler SDK. For instance, PGI implemented the CUDA Fortran on top of libNVVM, or OpenACC compilers will be implemented on top of the libNVVM we are providing. Another thing is to implement domain-specific languages on top of libNVVM, on top of the compiler SDK suite. So here you see some examples. MATLAB, for instance, R as a heavily used statistical language. JET is an DSL for fluid dynamics, developed by the double negative company. Halide is an image processing DSL developed from MIT. And there are a lot of progress in implementing DSLs on top of this compiler SDK. And of course, as I mentioned, enabling other platforms, other backends, so that you can use the libcuda lang from the NVCC compiler and to implement other backends, like in this case, the x86 backend. Enabling research in GPU computing. Of course, you can write your own language and use the CLang front end from the LLVM backend, and together with the CUDA SDK, compiler SDK, you can develop your own custom runtime. And it's interesting to see how many, especially academic institutions, are using this compiler suite or this compiler SDK, and we will see in the next time a lot of good results and good progress regarding the ecosystem. Some words about new developments in OpenACC. If you might have heard that the OpenACC consortium has presented a proposal for additions at the Supercomputing 2012 last November, and this proposal addresses a lot of issues we have maybe currently with the CUDA, with the OpenACC 1.0 version, but addresses especially new features which are needed with the OpenACC implementation. So, for instance, nested parallelism or function calls or better data directives for controlling unstructured data, deep copies, etc., multiple devices, profiling interface, and also addresses a certification test suite for OpenACC, which should be developed. You can find this proposal for additions for OpenACC 2.0 at the openacc.org website. There is a growing number of OpenACC supporters, so Alenia, Rugwave, Sandia, Oak Ridge, CSCS, Technical University of Dresden, Houston, Georgia Institute. If you are interested to work in the OpenACC consortium and to collaborate with these members here and supporters, don't hesitate to contact us or the OpenACC consortium directly. Last but not least, the most important point is, of course, the availability of applications for GPUs. So it's very difficult to follow all the GPU implementations and benchmarks and something like that. So we have an catalog, an application catalog available. You can find this on the Nvidia website, apps catalog, and this application catalog gives you the latest status about the GPU implementation, which describes you the features which are GPU implemented or accelerated, which describes the speed up we have seen for these kind of functions, and gives you a good overview and gives you also some more pointers where you can get more information about the GPU status for these applications. In summary, the Kepler architecture focuses on performance, efficiency, and programmability. The Nvidia parallel computing platform is evolving. One of the very important points is the open compiler architecture and the compiler SDK, which plays a very important role to broaden the GPU platform. And more important is the availability of GPU accelerated applications in academia and also in industry. That's all. Thanks, and I'm open for questions.